So anions form when an atom gains electrons. And so to write an electron configuration for an anion, we're going to take the atom's electron configuration and add electrons. Cations form when an atom loses electrons. So adding the electrons for an anion is straightforward. You just add them in. For cations, it's a little bit trickier. So for the main group elements, we're going to remove electrons in the reverse order of filling. And so for aluminum, it fills 1s2, 2s2, 2p6, 3s2, 3p1. So removing electrons, we're first going to remove this last one. We're going to remove 3 of them because it's making a +3 ion. So I'm going to remove that one first, and then those. And so I'm left with 2s2, 2p6. So the main group ones follow the pattern nicely. The transition metals do not. So for transition metals, we need to remove the valence electron first, even if it's not in the reverse order of filling. So if we look at iron, here's an electron configuration for iron. And where are the valence electrons? What level? What's the highest big number there? 1, 2, 3, or 4? 4 is the biggest number, right? These are the valence electrons in the middle there. In the hotel, it's the highest floor that has anybody staying on it. The 4th floor has 2 electrons on it. They went into that room before these guys went into the 3D room because this was cheaper. But this is still the highest floor, and that's what valence electrons are. So when iron loses electrons, it does not lose these that were added last. It loses the valence electrons first. So we're going to get rid of those first, and then we're going to get rid of them in reverse order. So we get rid of those 2, that gives us an iron 2 cation, and so here we've got this electron configuration. The 4s is gone because it doesn't have anything in it. And then if we want to make an iron 3 cation, we're going to take 1 off this last group here, this last sublevel, and make that a 5. So actually, let's do this because we can. So let's start with iron, 1, 2, 3, 4, 5. Oh, I got 1 too many. There, is that right? I'm doing this up here. Let's erase that too. So looking at the neutral atom, we've got 4s2 and 3d6. So when this becomes an ion, we're going to take out the valence electrons first. So I'm going to take this one out. Now it's a +1 ion. I'm going to take this one out. Now it's a +2 ion. And then I'm going to go into the 3D. I'm going to take this one out. And that's kind of a pleasing orbital diagram, right? The 4s is empty, and the 3D is half full. That looks nice. Any questions? So transition metals take the valence electrons off first. Most of them have 2 valence electrons. So some substances are magnetic. They will be attracted to a magnet, and others are not, right? Not all metals will have magnets stick to them. So we say that an atom or an ion is paramagnetic if it has unpaired electrons. It's diamagnetic if all the electrons are paired up. Paramagnetic species are attracted to magnetic fields, and the reason is having at least one unpaired electron. That unpaired electron generates a magnetic field, and that magnetic field is what's attracted to the other magnetic field. In a diamagnetic, atom or ion, all of the electrons are paired up. There are none that are spinning by themselves, and so it's not attracted. In fact, it's slightly repelled by a magnetic field. So the trick here is to remember which one's paired up and which one's not paired up. And what bothers me is this is paramagnetic, right? Sounds like pair, but it's not spelled P-A-I-R, right? That's not P-A-I-R. I'm writing with the eraser. No, para. No, it's spelled wrong. So that's not paired up. Di is a prefix that means two, right? Think of Noah's Ark. The animals came in 2 by 2, right? Diamagnetic, all the electrons are 2 by 2. They're all paired up. Okay? Write the electron configuration and orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. The electron configuration doesn't do a good job of telling us. We have to think about it too hard. The orbital diagram is what shows us whether it's paramagnetic or diamagnetic. So let's look at cobalt. So the previous noble gas for cobalt is argon. So we got argon. And then after argon, we've got 4s2 and 1, 2, 3, 4, 5. Is that 7? Cobalt 7. It's 3d7. That's neutral atom. Okay? To make a +2 ion, what do? I remove how many electrons? 2 electrons. Which ones do I take off? The ones with the highest quantum number, the valence electrons, because this is a transition metal. So I'm going to lose those guys. I'll take those guys out. So its electron configuration is argon 3d7. And then we're supposed to do orbital diagram. So that was 4s. Here's 3d. And it has 7 electrons in the 3d. 1, 2, 3, 4, 5, 6, 7. Are there unpaired electrons? Yes. So is it diamagnetic or paramagnetic? Paramagnetic. They're not going 2 by 2. Diamagnetic. So this is paramagnetic. This would be attracted to a magnetic field, because moving charges generate magnetic fields. These electrons aren't paired up with another electron of an opposite spin. Okay, let's look at nitrogen. So, nitrogen, the previous noble gas is helium, which is a little silly, but helium, and then we've got 2s2 and 2p3 for the neutral. So we start with the neutral atom, and then the 3 minus tells me I need to add 3 electrons. So I'm going to add them here, and I'm going to get 2p6. And then we can draw an orbital diagram for those valence electrons. So there's 2s, and there's 2p. We've got 2 electrons in there, and 1, 2, 3, 4, 5, 6 in there. Paramagnetic or diamagnetic? Diamagnetic. Di means 2. 2 by 2. They're all 2 by 2. There's the elephants and the giraffes and the beavers and the skunks. Diamagnetic. Any questions?
On the cobalt, why did we scratch out 4s?
Good question. Why do we take these off? Because the valence electrons are the ones that are the furthest out. And so those are the ones that get removed. Transition metals, we're always going to remove the valence electrons first. So the 2 plus means it lost 2 electrons. And we're going to take the valence electrons off first. If we needed to take more off, then we take them out of this 3D sublevel. Any other questions? Continuing to talk about ions, how do they compare in size? Well, cations are much smaller than neutral atoms because when you form a cation, generally you've lost all the valence electrons. You took the entire outer layer off. Now some of those core electrons are the new valence electrons, which means that the number of core electrons has gone down, the effective nuclear charge has gone up, and so they actually get much smaller when they become cations. So here's sodium and the sodium ion, 186 down to 95 picometers. It's almost half the size. So this is why, but I think remembering are cations smaller or bigger than atoms is easy because if you're taking something off, does that make it smaller or larger? It makes it smaller, so it makes it smaller. Anions are much larger than neutral atoms, and that makes intuitive sense too because if you're adding stuff onto the outside of the atom, that should make it bigger, right? That doesn't explain why it gets so much bigger, but it does. It gets a lot bigger, and so we see that there's this huge jump in size when we add some electrons. We're adding electrons without adding any more protons, and so the effective nuclear charge becomes lower, and that lets the atom expand out. So we can look at isoelectronic ions. So iso is a prefix that means the same electrons. So these are ions with the same numbers of electrons. So here's a series of them. Sulfide, chloride, potassium, and calcium. They each have 18 electrons. Sulfur has 16 protons. To get the -2 charge, it gained 2 electrons. It's got 18 electrons. Chlorine gained 1 electron from 17 protons, now has 18 electrons. Potassium lost an electron. It has 19 protons with 18. And calcium lost 2 electrons. So what we see is that the anion is bigger, and the larger the charge on the anion, the larger the size. So 184, 181, and then it drops 133 and 99. They have the same number of electrons in the same configuration, but what's different is the nucleus. So we have differences in the nuclear charge. So higher nuclear charge, smaller atom or ion. So choose the larger atom or ion from each pair. So potassium atom or potassium ion, which is bigger? The atom. Because when you make the ion, you're taking electrons off. And I don't know about you, but if I peel an orange, it gets smaller, right? It doesn't get bigger. Fluorine or fluoride? Fluoride. Because here we're adding something. We're putting something on the outside, it gets bigger. And this one requires a little more thinking. Calcium or chlorine? Calcium ion or chloride ion? Well, you might think they're the same, but they're not. So before we start even thinking about whether we can answer that, we need to make sure that those have the same number of electrons, because otherwise we can't really compare them very well. So chlorine has 17 electrons, and it's gained 1, so it's got 18 electrons. Calcium has 20 as an atom, and it lost 2. So these are isoelectronic. They each have 18 electrons. Calcium has 20 protons, and chlorine has 16 protons. Which one's going to pull the electrons in tighter? Pull them in tighter would be the calcium, right? So calcium's got more charge on the nucleus. It's going to hold on to its electrons tighter, making it smaller, right? So the chloride ion is larger. It weighs less, but it's bigger. Any questions?